Hello, and welcome to this presentation on hierarchical kickstarting for skill transfer in reinforcement learning. And this is a paper for the first conference on lifelong learning agents. So I want to start this presentation by giving a motivating example of a tricky environment for reinforcement learning. So this is the so-called SeaMonsters environment, which is implemented in the game of NetHack. So as you can see, our character exists on a 2D grid in which the aim is to reach the downward staircase. Now our action space consists of 32 discrete actions, which includes 16 movement actions, which correspond to the cardinal directions and the diagonals. And for each of these directions, we can execute either a one-step move or just a long move until we bump into something. And we also have a set of 16 miscellaneous command actions, which allow us to interact with various items and entities in the game. So the environment is episodic. And as previously mentioned, the aim is to reach the downward staircase on the right bank. And doing this will terminate the episode and give +1 reward. While on the other hand, dying in the game will give -1 reward while also terminating the episode. So you might be looking at this and thinking, what seems so hard about this environment? I mean, you can't walk over the water, but we can see that there's a path through it. So I'm now in the environment controlling the character. Now, the first thing you might notice is that it looks a bit different to the image in the presentation. This is because it's a procedurally generated level, so it looks a bit different every time. Now you can see what happens if I just try and walk across the path. I don't last very long because there are piranhas in the water and they kill me. So in order to survive, I have to make use of this armor piece that's on the floor. So I can pick up the armor piece by pressing comma. I then remove the current armor I'm wearing by pressing Shift-T, and then I wear the armor I picked up by pressing Shift-W followed by F. So now I'm wearing this very powerful suit of armor, and I can walk across, and the piranhas can't hurt me. I can make it to the staircase. So we can see now why this is such a tricky environment. So we have to execute a very precise set of steps before our reward function gives us any indication that we've done something good. Not only that, but in training, the agent will likely learn to stay away from the bridge, as early on in training, when it hasn't put the armor on, it will just keep dying to the piranhas and see there's a negative reward on the right-hand side, so it will try and keep away from it. So, sparse reward problems are quite a well-studied area. So a few methods some people have come up with is reward shaping is perhaps the most commonly used. So in our example of the SeaMonsters environment, we could give some rewards along the way for picking up the armor, taking off your armor, putting it on to kind of guide our agent along the right path. There's curiosity-based methods where the agent is intrinsically encouraged to explore more. We have curriculum learning, where rather than just learning on this single quite hard environment, we would construct some easier environments for the agent to first learn on and kind of get a good kind of base policy before we work up towards the harder environment. And there's also auxiliary tasks, where we also ask the agent to predict other values, and this has been found to help with representation learning. So finally, I want to show you the relatively unexplored area of using pre-trained skills, which I'm going to argue should serve as an additional tool in the tool belt of RL practitioners. So you're probably wondering now, what's a skill? So I would define it as a policy that manifests some useful change in the environment. So for a concrete example, using our SeaMonsters task, we can imagine that we have the SeaMonsters task here, and then this could kind of be split up into a number of skills, which together can be solved to complete the environment. So clearly kind of the level of granularity of these skills and how we split them is fairly arbitrary. Here I've split them in a way that kind of would make sense to humans. But yeah, again, it's a fairly arbitrary choice of how we split these. Okay, so now we know vaguely what skills are. You might be wondering, where would we get them from? So one way is from a unsupervised search for diverse policies. So this is kind of nice and automatic, but the quality of these, might not be great. We could imagine this unsupervised search finding a lot of useless skills, which we're going to have to sift through later when we make use of them. An alternative is handcrafting heuristic policies. So this isn't the focus of this paper, but I actually think this is a really promising area. So for an example, you can see in the NetHack challenge at Europe's recently, deep RL methods performed significantly worse. The best deep RL method was significantly worse than the best method that was just, symbolic, hard-coded AI, people just writing their own heuristics. So I think using handmade skills could actually be, a potential path forward there. But what we'll be looking at in this paper is training skills with reinforcement learning on handcrafted skill acquisition environments. And here I've shown you the 4 environments that could be used to train skill policies for SeaMonsters environment. So these are all, obviously, in NetHack they have the same observation space, the same action space, but they've been made such that solving these environments will teach the agent how to do a specific skill. So I think we now understand what skills in this context are. They're essentially just policies that solve some part of a task, and hopefully we now understand how we could get them. So what we mean when we say skill-based learning is that we're training with reinforcement learning, but we have this additional prior knowledge in the form of useful policies. So the question now becomes, how do we make use of these policies? So one way to make use of these pre-trained skills is with the options framework. So in the options framework, in this example here, so we have an environment like we usually do, and you can see I've put some subtasks in it. So this is, the environment's just the same as normal. This is just kind of hammer home the point that this task can kind of be decomposed into these smaller tasks that might be able to be solved by so-called skills. So if we look at the full architecture, so we can see we've got these things called options. So what these are is that we would substitute in our pre-trained skill policies into these options here. And then we have a so-called policy over options, which at every time step takes the observation and then decides which option it wants to execute at that time step. And we can see that the little lock sign is meant to represent that the options are frozen, the weights in those are frozen, so all we can learn is which option to take. We're not changing our options as we train. And there are work has been done on training options simultaneously with policy over options in the option critic architecture, but yeah, we're not looking at that. So in a way, in this setup here, you could see as the options as sort of being just like the actions of the policy over options which we're training. So it's sort of like we've abstracted the actions and reduced our action space massively. So the big kind of disadvantage of this system when you can't train the options is that we can't learn sort of beyond the skills. Like if there was something needed to solve the task that was missing in our skill set, we're not going to be able to solve the environment, sadly. So another approach is kickstarting reinforcement learning. So again, we have this environment which we've split into subtasks, but in this one we actually have an agent just like normal, which learns from the extrinsic reward signal. So right now this looks like just regular reinforcement learning. So the bit that kickstarting adds is this little extra loop. So you can see again we have our pre-trained skill policies, except rather than calling them options, we now call them teachers in this architecture. So at every time step, each teacher takes in the observation and produces an action distribution. And then we can see these action distributions are then averaged, and then we have this knowledge transfer to the agent. So what this means is that the agent incurs a loss for how much its own action distribution deviates from the mean of the teacher action distributions. So it's kind of like the agent, as well as learning from the extrinsic reward, is also being nudged to act a bit more like the teachers. So the idea is that this will kickstart the agent into a useful policy by kind of encoding this prior over the action distributions condition on the state. So this kind of overcomes the problem we were saying with the options framework in that we can learn beyond the teachers. The agent is very capable of learning its own policy, especially if we kind of decrease the influence of the teachers as time goes on. I think the big problem here, you might think, is that we're not really using the teachers very intelligently. We're just taking the mean of them. And if you think about the SeaMonsters environment that we talked about earlier, at a given time step in the episode, it's likely that only one teacher is going to be relevant. So when the agent needs to pick up the armor, the skill policy for picking up the armor will be having some influence, but so will all the other skills, and they might drown it out a bit, essentially. So I should note here that the Kickstarting paper does propose using population-based training to give an individual coefficient to each teacher. However, these coefficients, they vary over much larger timescales, over epochs. They still remain constant within an episode. So while this is, a useful addition, it doesn't get around the fundamental problem here. So if we take a closer look now at the Kickstarting loss, we can see we can kind of break it down into three parts. So we've got the Kickstarting coefficient. So this is just, how much does this loss influence our total loss? So as we said before, we might like this to start quite high. So at the beginning, we'd like the teachers to be influencing the agent a lot, but as we go on and the agent's kind of learning its own better policy, we'd like this to decrease and drop off. And what actually is the loss? So it's just the cross entropy of the agent policy to the mean of the teachers, like we said. So if the agent is perfectly following the mean of the teachers, then this will be 0, and it will be maximized when the agent is completely disobeying the teachers and doing something completely different. So we now come to our proposed new algorithm, which we've called Hierarchical Kickstarting. So similar to Kickstarting, we have an agent which interacts, normally with the environment. And again, kind of the addition of Hierarchical Kickstarting is this knowledge transfer, is this additional loss. But the difference between this and Kickstarting is that rather than taking the mean, we have an additional policy, which we've called the policy over teachers. And what this does is it weights each teacher at every time step. So we're going for a weighted mean that is conditioned on the state, which means that our policy over teachers can learn to prioritize different skills at different times, as opposed to Kickstarting, where it's held constant. The weights are held constant throughout an episode. So you should note here that while the teachers, as per usual, are frozen, both the agent and the policy over teachers, their weights are both unfrozen, so these will simultaneously learn during training. So you can imagine the way this works is that agent learns from the extrinsic reward, but also from the additional Kickstarting loss, while the policy over teachers only learns from the Kickstarting loss. That's, the kind of extrinsic loss isn't propagated through in any way. So we have an agent, learning to try and do well in the environment while simultaneously trying to listen to this weighted mean of teachers. So, it's kind of striking a balancing act between them. And then on the other hand, we have the policy over teachers, which is simultaneously trying to learn, but all it's trying to do is just match what the agent's doing. So what this means is that given a particular state, it tries to predict, what combination of teachers of skills the agent actions will look most similar to. So you can kind of see this is an additional level of bootstrapping here, but we'd imagine that the incentives are here for these policies to kind of quickly converge and fall in line with each other, where the agent is performing actions similar to the policy over teachers, and the policy over teachers is recommending teachers similar to how the agent acts. So if you squint very hard, you might be able to see this as sort of a combination of kickstarting and the options framework, and we'd like to think that you kind of take the positives of both of them. So yes, we have this lovely new algorithm that we want to try out, but it turns out that not that many environments are actually easily suited to the process of making these skill acquisition environments in their frameworks. So we decided to make our own, and this is what SkillHack is. So SkillHack is a benchmark of skill transfer and reinforcement learning. It consists of 8 task environments, which you can see here, with the SeaMonsters task being one of them, and 16 skill acquisition environments. And this is all made using MiniHack, which itself is based on the NetHack learning environment. So all the game mechanics of NetHack are kind of what builds this up. So the features of SkillHack, it's got sparse rewards, as mentioned before. All 8 of the task environments shown here. They're just like SeaMonsters. You get +1 reward for winning, -1 reward for dying, and that's it. So they're all procedurally generated. So this has been shown to improve generalization, and it means that we learn reactive policies, not just memorizing a list of actions. So it's very fast, based off NetHack learning environment, and stochastic. All the environment dynamics are from NetHack, which is intrinsically stochastic. So you attack a monster, there's a chance you might miss. And it has a very large state action space. We've got 32 actions, as mentioned before, and the state space is kind of an encoding of these images that you see here. We don't feed in pixel values, although that is an option. We didn't go there. And yes, many of the skills are shared between many of the tasks. So 8 tasks, 16 skills, but most of the tasks have 3 or 4 required skills to complete them. So we have our benchmark, and we have a bunch of algorithms, so I think now we need to see how they do. So to briefly go over our experimental setup, we used Impala as the underlying algorithm for everything, and specifically we used the TorchBeast implementation. So we use this to pre-train the 16 expert skill policies on the skill acquisition environments. And then we then ran experiments on all 8 of the task environments. So specifically, we ran the vanilla Impala agent. We also ran random network distillation, which is an algorithm made specifically to target sparse reward problems. We implemented the options framework and kickstarting, and of course, finally, hierarchical kickstarting. So I've shaded in blue the algorithms that didn't make use of the skill expert policies, and red are the ones that did. So the results, as you can see here, this is averaged over all 8 of the environments. So I think the first thing to notice is that vanilla, RL, and RND, the 2 algorithms that didn't make use of the skill policies, they both just completely failed to learn. They were just defeated by the sparse rewards. So after that, you can see the options framework did the next best. I think surprisingly well, considering that it couldn't do anything that wasn't specified in the skill policies. And then a bit higher, we have kickstarting, and then best of all was hierarchical kickstarting. So while I think those results are interesting, I think it's more interesting to kind of dive in and see what's actually happening. So here we have the so-called prepare for battle task. So what you have to do here is you have to pick up this cloak and put it on, and then you have to go and eat the apple. So if you're wondering, and that's the diagram, if you're wondering why you don't have to pick up the apple, it's because you just eat it off the floor. So this graph shows the output of the policy over teachers for a single episode for our converged agent. So as we can see, the output of the policy over teachers changes over time as the state changes. So if you can imagine what these lines would effectively look like for kickstarting, is they'd just all be horizontal lines all at 33%. So if we kind of want to dive into what this graph's actually showing, we can see right at the beginning, we're prioritizing the pickup skill most of all. So this is right at the beginning of the episode, and in this episode, you know, it can do these two things in any order, but it decided to go for the cloak first. So the first thing it's saying to do is pick up. So you know, within a few time steps, we've gone and picked up the agent, the cloak, and now the policy over teachers is saying, okay, the next thing you need to do is to wear this cloak, and we see we have a period where it's recommending wear as the highest value policy. And then once the agent has put on the cloak, we can see it's recommending to go and eat the apple as the highest value skill to do. So we can really see that the policy over teachers has, you know, it's fallen in step with the agent's policy, and it's recommending exactly what the agent needs to do, and the agent itself will be following what the policy over teachers is recommending it to do. So in conclusion, so I hope I've convinced you that pre-trained skills can provide a useful bias for sparse reward problems, and, you know, and I really think in the future they can be, like I said before, an additional tool, the tool belt of us RL practitioners. I've also presented Hierarchical Kickstarting, which is a new method for making use of expert skill policies, and also Skill Hack, which is a benchmark for evaluating all of these skill-based methods. So for more detail, please see our paper. It has the same name as this presentation. And a bit of final info, will be at the poster session virtually on the 18th and 19th of August at the times said there. The code is available here, and if you missed the poster session, or you're watching this after the poster session, that's my email if you want to ask me any questions about this. So thank you very much for listening. I'd like to thank my collaborators. I'd like to thank everyone who reviewed the paper, and of course the organisers of the conference. And here are the references. Thank you very much for listening.